Hello everyone, I am Pragati Paurel and today I will be presenting my MSc research on crop disease detection using convolutional neural network and vision transformer, which was supervised by Dr. Moez Maharzan. Let me begin by giving you a brief overview of the problem and why this research matters. Agriculture plays a very critical role in ensuring global food security. However, crop diseases remain a major challenge, causing severe losses in both yield and quality. Traditional methods of disease diagnosis rely heavily on human expertise, which can be subjective, slow, and not scalable, especially in large or remote farming setups. With the rapid evolution of AI, particularly in the deep learning, we now have models like convolutional neural networks and vision transformers that can analyze plant leaf images and detect diseases automatically with high accuracy. These technologies, especially when deployed via mobile devices and drones, are changing how we manage diseases, enabling early detection and timely intervention. Therefore, the core aim of this research was to investigate how effectively CNN and VITs can identify plant diseases from leaf images. To accomplish this, I had three main objectives. First, I aimed to assess and compare the performance of CNNs and VITs using publicly available dataset. I wanted to see how well these models performed across various plant species and disease types. Second, I conducted a comparative analysis focusing on key metrics like classification accuracy, computational efficiency, and generalization ability. Finally, I evaluated the feasibility of deploying the best performance model as a web-based tool for practical use in resource-constrained environments. Next, I will explain the rationale behind choosing CNN and Vision Transformer for this task. The rationale for this study is grounded in a real-world problem. Plant disease not only reduce productivity but also hard to detect accurately using manual methods. Farmers often have limited access to expert or agronomists, especially in rural areas, making disease misdiagnosis common. CNNs have already demonstrated potential in automated image-based disease detection. However, they tend to focus on local features, which can be limiting when disease symptoms are scattered. That's where Vision Transformer offers a potential edge. They can model global context and long-range dependencies, which is crucial for recognizing irregular disease patterns. This resource explores whether VITs, especially pretrained ones, can outperform CNNs and lead to more robust and generalizable disease detection systems. Before diving into the methodology, it's important to consider what previous research has been done and so on. The literature review shows a growing trend on the use of the deep learning in agriculture, particularly for the plant disease detection. CNN have been widely applied and are known to detect visual symptoms such as spots, fungus growth, and discoloration with high accuracy. A study by Hossein et al. At 2022 demonstrated this in wheat disease classification. However, recent research by Khan et al. At 2022 and Thakur et al. At 2023 indicates that Vision Transformer can outperform CNNs in many image recognition tasks. VIT models and image as a sequence of patches and capture both local and global patterns using self-attestation mechanism. This makes them especially effective in detecting distributed symptoms. Explainable AI like GradCam also enhance model interpretability by visually highlighting which regions of the leaf contributed most to the prediction, an important factor for building trust among user and experts. Furthermore, mobile and edge deployment is gaining traction, allowing real-time in-field diagnosis, transforming agriculture into a more responsive and sustainable practice. Now, let's move on to the methodology, how I prepared the data, selected and trained the models, and evaluated their performance. For this study, I utilized the new plant village dataset, from Kaggle, which comprises 83,430 labeled images of healthy and diseased leaves from multiple crops. It consists of around 66,745 training images and 16,685 of the validation images. The step-by-step breakdown of the methodology is: first, data collection and pre-processing, where images were cleaned and resized. They were also normalized to ensure model stability during training. Second, model selection, in which I trained a CNN from scratch, designed specifically for the dataset. I also trained a vision transformer from scratch with default hyperparameters. Finally, I utilized a pre-trained vision transformer that had already learned rich and generalizable image features from a large-scale ImageNet dataset through transfer learning. Third, training and evaluation, where each model was trained and monitored using metrics like validation accuracy, loss, and F1 score, and at last, web application development. To demonstrate deployment feasibility, I developed a user-friendly web app using Streamlit, an open-source Python framework. The app allows users to upload a leaf image and get instant disease predictions. With the methodology explained, let's look at the result and what they mean. The results from the training phases are quite revealing. The CNN model, trained from the scratch, achieved 98.93 validation accuracy and had a F1 score of 0.99, indicating consistent and accurate learning. The Vision Transformer model, that was trained entirely from the scratch, performed notably poorly, achieving an accuracy of only 3.02%. It faced significant challenges in learning meaningful patterns from the data and struggled to converge during training. This underperformance is likely because VIT typically require a very large amount of data to effectively learn useful representation, and without the benefit of pre-training on a large diverse dataset, the model was unable to generalize well or capture the complex features needed for the accurate predictions. The pre-trained VIT significantly outperformed both, reaching 99.32% validation accuracy with the fast conversions and similarly high F1 score of 0.99. From the training plots, we can observe that the pre-trained VIT had a steep accuracy curve and low validation loss, demonstrating both efficiency and robustness. It performed better primarily because it leverages transfer learning, which means it starts with the knowledge gained from the training on a large, diverse dataset. This pre-training allows the VI to already understand fundamental features like ages, textures, shape before being fine-tuned on the specific task of the plant disease detection. Unlike training of VIT from the scratch, which requires vast amount of data and time to learn meaningful representation. The pre-trained model can quickly adapt to the new dataset, leading to faster convergence and higher accuracy. This confirms that transfer learning is crucial when working with the smaller or domain-specific datasets, such as plant leaf images. One of the key outcomes of this project is the deployment of web-based application designed to bring our resource findings into practical use in the real-world setting. This image was constructed using Streamlit and incorporates the best performing model, which is the pre-trained VIT. Users can easily upload images of plant leaves, and within minimum moments, the app provides a predicted classification of any disease present. This rapid response is crucial for effective disease management, enabling users to take timely action. Furthermore, the application also offers practical guidance and recommendation for the managing the detected disease, ensuring users have access to necessary information for the effective treatment of the disease. The interface is thoughtfully designed to be simple, intuitive, allowing it to be deployed on various platforms, whether cloud-based or on local machines. This user-friendly approach guarantees that even individuals with minimal technical knowledge, such as farmers, can utilize the tool effectively and confidently. This application has the potential to revolutionize disease management in the agriculture sector by providing fast, accurate, and accessible diagnostics. It can significantly benefit low resource settings where timely and accurate information is crucial for maintaining healthy crops and improving farmers' livelihood. By bridging the gap between resource and practical solutions, this tool stands to make a meaningful impact on agricultural productivity and sustainability. To summarize this study confirms that pre-trained vision transformer outperformed CNN and untrained VITs in plant disease detection tasks. They offer better generalization, faster convergence, and higher accuracy. By combining this model with an easy-to-use web-based application, we can bridge the gap between cutting-edge AI and real-world agricultural needs. This resource contributes to developing scalable, sustainable, and intelligent disease management solutions for the agricultural sector. Finally, I want to discuss the ethical consideration that guided this work. Me, while developing this AI-based system, I compiled with several ethical concerns, where the training dataset was kept diverse to reduce algorithmic bias and improve fairness across different crops and diseases. Importantly, the tool is meant to support, not replace, expert human judgment. I also ensured that users are clearly informed about the limitation of the model, promoting transparency and responsible. Lastly, I would like to express my deep gratitude to my supervisor, Dr. Mohesh Maharjan, for his unwavering support and throughout this project. Additionally, I would like to thank the British College for providing the resources and platform necessary for this research. Thank you all for listening. If you have any questions, feel free to reach out to me at the email address provided.